Hello, friends. Take a look at this number line. Every point you see on it, the whole numbers, the fractions, the decimals, even strange ones like pi and the square root of 2, they all live on this single unbroken line. We call this the real numbers, written as R. But here's the thing. Once you have all these numbers, you start needing ways to talk about groups of them. Not just one number, but a whole stretch. Numbers bigger than 5, numbers between 0 and 1, numbers that satisfy some condition. That's where intervals and inequalities come in. They're the language we use to describe pieces of the number line. And in this video, we're going to break down exactly how that language works, what real numbers really are, how intervals carve them up, and how inequalities let us pin down the slice we care about. Let's start with the number line itself. All right, here's the number line. It's a simple idea, but it's doing a lot of work. Every real number, and I mean every single one, has exactly one spot on this line. Pick a number, and there's a point. Pick a point, and there's a number. 0 sits in the middle. To the right, numbers grow bigger and bigger, going on forever. To the left, they go negative, also forever. Those little arrows on the ends, they're a reminder that the line never stops in either direction. Now, notice what's between the integers. Numbers like 1/3, or root 2, or pi. They're not whole numbers, but they're real numbers, and they each have their own exact spot on the line. In fact, between any 2 points you pick, no matter how close together, there are infinitely many more numbers squeezed in between. The line isn't just dotted with numbers. It's packed with them, with no gaps anywhere. So when we say real numbers, this whole continuous line is what we mean. But not all real numbers are the same kind of number. Some are tidy, and some are a little wilder. Let's look at the different families that live on this line. Think of the real numbers as a big family. And inside that family, there are smaller groups nested within each other. At the very center, you have the natural numbers, 1, 2, 3, 4, and so on. These are the counting numbers, the ones you'd use to count apples or steps. We write this set as n. Wrap a bigger circle around those, and you get the integers, all the naturals plus 0 plus their negatives. So now we've got things like -3, -2, -1, 0, 1, 2, 3. We write this as z. Go one circle wider, and you get the rationals, written as q. A rational number is anything you can write as a fraction, one whole number divided by another. So 1/2 is rational. So is -3/4. So is 7, because 7 is just 7/1. Even decimals like 0.75 are rational, because 0.75 is the same as 3/4. Now here's the interesting part. You'd think rationals cover everything, right? But they don't. There are numbers on the line that cannot be written as a fraction, no matter how hard you try. Numbers like pi, or square root of 2, or e. We call these the irrationals, and when you add them to the rationals, you finally get the full set of real numbers, real. So the real numbers are everything. The naturals, the integers, the rationals, and the irrationals, all sitting together on one continuous line. But what makes irrational numbers so special? And how do we know they really can't be written as fractions? Let's take a closer look. Here's the cleanest way to tell rationals and irrationals apart. Look at their decimals. A rational number, when you write it out as a decimal, either ends or repeats. Take 1/2. That's just 0.5. Done. Take 1/3. That's 0.3333 with the 3 repeating forever. Take 2/7, and you get a longer repeating block, 285,714, that just keeps cycling. But there's always a pattern. Sooner or later, the digits settle into something predictable. An irrational number does neither. The decimals go on forever, and they never fall into a repeating pattern. Look at pi, 3.14159, and on, with no block of digits ever cycling back. Same with the square root of 2. Same with e. They're not random in the everyday sense, but they never repeat. Now, you might be thinking, Okay, but how do we know a number like the square root of 2 can't be written as a fraction? Maybe we just haven't found the right one yet. Here's the beautiful part. We can prove it. Suppose, just for a moment, that the square root of 2 could be written as a fraction, p over q, in lowest terms, meaning p and q share no common factors. Square both sides, do a little algebra, and you can show that p has to be even, which forces q to also be even. But wait, we said they share no common factors. Contradiction. So our assumption was wrong. The square root of 2 simply cannot be written as a fraction. Ever. That's the kind of thing that makes irrationals feel almost mysterious. They're real. They have an exact spot on the number line, but they slip through the net of fractions entirely. Okay, so now we've got a handle on what real numbers are. Let's start carving up the number line into pieces. That's where intervals come in.
All right. An interval is just a stretch of the number line, a continuous slice. Pick a starting point, pick an ending point, and an interval is everything in between. Look at this one. We've highlighted the chunk from 2 to 6. Every single real number sitting in that blue strip, 2 itself, 4.7, 5.999, 6 itself, they're all part of the interval. Anything outside that strip, like 6.1, is not in it. The notation we use is square brackets, 2, 6. The square bracket means include this endpoint. So 2, 6 is read as all real numbers x, where x is greater than or equal to 2 and less than or equal to 6. That's a closed interval. Closed because both endpoints are part of the set. Notice the solid dots at 2 and 6? Those filled-in dots are the visual signal that the endpoints are included. Bracket on the page, dot on the line. Same idea. But what if we don't want to include the endpoints? What if we want everything between 2 and 6, but not 2 or 6 themselves? That's where the notation has to change a little, and that's what we'll look at next.
All right, here's where the notation gets a little more expressive. Watch the brackets carefully. Each one is telling you something specific. Up top, we've got an open interval, written with parentheses, parenthesis 2, 6. That parenthesis is saying don't include the endpoint. So this is every number strictly between 2 and 6, but 2 itself and 6 itself are out. The hollow circles at the ends are the visual way of saying the same thing. The endpoints are excluded. In inequality form, this is 2 less than x less than 6, strictly less than on both sides. The middle one is a mix. Square bracket on the left, parentheses on the right. Square bracket 2, parentheses 6. That means 2 is included, but 6 is not. Solid dot at 2, hollow circle at 6. The inequality is 2 less than or equal to x less than 6. Less than or equal to on the left, strictly less than on the right. The bottom one flips it. Parentheses 2, square bracket 6. Open on the left, closed on the right. So 2 is excluded, 6 is included. The inequality is 2 less than x less than or equal to 6. So the rule is simple. Square bracket and solid dot mean included. Parentheses and hollow circle mean excluded. That's the whole grammar, and once you've got it, you can read any interval at a glance. But what about intervals that don't have a right endpoint? What if we want every number bigger than 5, going on forever? For that, we need to bring in infinity.
Sometimes we want to talk about all the numbers bigger than something, or all the numbers smaller than something, with no upper or lower limit at all. For that, we use the infinity symbol. Look at the top one, 3 infinity. This is every real number from 3 onward, going right forever. The square bracket on the left means 3 is included, solid dot. The parentheses on the right next to infinity means, well, here's the key idea. Infinity isn't a number. You can't actually reach it. It's more like a direction, a way of saying keep going, no stopping point. So we never put a square bracket next to infinity. It's always a parentheses, always. The middle line is almost the same, but with a hollow circle at 3. That's 3 infinity. Every number strictly greater than 3, but not 3 itself. The inequality is x is greater than 3. And the bottom one goes the other way. Negative infinity, 3. Every number from negative infinity up to and including 3. Solid dot at 3, arrow extending left forever. The inequality is x is less than or equal to 3.
So infinity gives us a way to describe rays, half-lines that stretch off without end. Combine that with the bracket grammar we already learned, and you can describe pretty much any stretch of the number line you want. But intervals are just one piece of the picture. Often what we really want is to find the numbers that satisfy a condition, like x squared is less than 9, or 2x plus 1 is at least 7. That's where inequalities come in. Let's see how to solve them.
All right, an inequality is just like an equation, except instead of an equal sign, you've got a less than or greater than. And the goal is the same. Isolate x. Figure out what values make the statement true. Let's solve this one. 2x plus 1 greater than or equal to 7. We want every value of x that makes the left side at least 7. First step, get rid of that plus 1. Subtract 1 from both sides. The left becomes 2x, the right becomes 6. So now we've got 2x greater than or equal to 6. Next, divide both sides by 2. Left becomes x, right becomes 3. So x greater than or equal to 3. That's it. Every real number that's 3 or bigger satisfies the original inequality. Plotted on the number line, solid dot at 3, blue strip extending right forever. In interval notation, that's 3, infinity. Notice what we did here. We treated the inequality almost exactly like an equation. Add the same thing to both sides? Fine. Subtract the same thing from both sides? Fine. The relationship between the two sides doesn't change. But, and this is important, there's one operation that breaks this rule. One thing you can do that flips an inequality on its head. And if you're not careful, it'll trip you up every time. Let's look at it next.
Here's the rule that catches people out. Watch what happens. We've got negative 3x less than 12. To isolate x, we need to divide both sides by negative 3. But the moment we do that, something changes. The inequality sign flips. The less than becomes a greater than. So our answer isn't x less than negative 4, it's x greater than negative 4. Why does this happen? Think about it on the number line. Take two numbers, say 2 and 5. 5 is bigger than 2. Now multiply both by negative 1. You get negative 2 and negative 5. And now negative 5 is smaller than negative 2. The order reversed. Multiplying by a negative number flips the entire number line. What was on the right ends up on the left, and vice versa. So any inequality between them flips too. The rule is simple, but it's ironclad. Whenever you multiply or divide both sides by a negative number, you have to flip the inequality sign. Less than becomes greater than. Less than or equal becomes greater than or equal. No exceptions. Plot the answer on the number line. Hollow circle at negative 4 because it's strictly greater. Blue strip extending right forever. In interval notation, negative 4, infinity. Now, we've solved a one-sided inequality. But sometimes you'll see something stricter, an inequality with bounds on both sides at once, like 1 less than 2x minus 3 less than or equal to 7. These are called compound inequalities, and they have a neat little trick to them. Let's look at one. A compound inequality is just two inequalities stacked into one statement. Look at this. 1 is less than 2x minus 3 less than or equal to 7. What it's saying is the expression 2x minus 3 is strictly greater than 1 and less than or equal to 7, both at the same time. We want every x that satisfies both conditions. The trick is you don't have to split them up. You can solve all three parts at once, as long as you do the same operation to every piece. Start by getting rid of that negative 3. Add 3 to all three parts. The left becomes 4, the middle becomes 2x, the right becomes 10. So now we've got 4 is less than 2x less than or equal to 10. Next, divide every part by 2. Left becomes 2, middle becomes x, right becomes 5. Final answer, 2 is less than x less than or equal to 5. Plot it. Hollow circle at 2 because x is strictly greater than 2. Solid dot at 5 because x can equal 5. The blue strip is everything in between. In interval notation, that's 2, 5. Open on the left, closed on the right. And the same warning still applies, by the way. If at any step you multiply or divide all three parts by a negative number, every inequality sign flips. Both of them. Always. So now we've got the toolkit. Real numbers, intervals, inequalities, and how they all connect. Let's tie it all together.
All right, let's pull it all together. First, the real numbers. Every point on the number line corresponds to a real number, and every real number sits at exactly one spot. That includes the integers, the rationals, and the irrationals, like pi and square root 2. The whole line, R, is one continuous gap-free set. Second, intervals. Intervals are how we describe a continuous chunk of that line. Square brackets and solid dots mean the endpoint is included. Parentheses and hollow circles mean it's excluded. And whenever infinity shows up, it always gets a parentheses, because infinity isn't a number you reach, it's a direction you head in. Third, inequalities. Inequalities are how we find those chunks. Solve them like equations, with one critical exception. Multiplying or dividing both sides by a negative number flips the inequality sign. Add and subtract freely, but the moment a negative shows up in a multiply or divide, flip it. Real numbers, intervals, and inequalities. They're really three different languages for talking about the same thing, pieces of the number line. Once you can move between them fluently, a huge amount of math suddenly becomes easier to read. From solving equations, to graphing functions, to defining domains and ranges, it all builds on this. If this video helped, hit like and subscribe to StemSift for more clear, intuition-first explainers. Thanks for watching, and I'll see you in the next one.